In the last lecture, we understood the shooting technique for solving linear boundary value problems with Dirichlet boundary conditions. We would demonstrate this method for some examples in this class. Let us consider a linear boundary value problem, which is governed by this differential equation for x in the interval 1 to 2. And the Dirichlet boundary conditions are y of 1 is 1 and y of 2 is 2. So, we would like to apply shooting technique to solve this linear boundary value problem, which in turn requires approximations of solutions to two initial value problems. So, we must define those two initial value problems. Let us do that. For the first initial value problem, the governing differential equation is the same as the governing differential equations for the linear boundary value problem, namely a non-homogeneous differential equation. So, we have written down the equation here in the interval 1 to 2. What should be the initial conditions for the first initial value problem? Take the left end condition that is prescribed in the boundary value problem and use this as an initial condition for the first initial value problem. So, it is y1 at 1 equal to 1. Since it is a first initial value problem, I call the unknown as y1. What should be y1 prime at this initial point 1? It can be arbitrarily prescribed. So, we prescribe it as 0. So, that defines the first initial value problem. So, it is clear. Let us now move to second initial value problem. What is it? The second initial value problem corresponds to the homogeneous differential equation which is obtained from the given linear boundary value problem. This is the non-homogeneous term. So, I must omit this term and consider the corresponding homogeneous differential equation that governs the boundary value problem. So, the equation that governs the second initial value problem is going to be y2 double prime equal to minus 2 by x y2 prime plus 2 by x square y2 for x in the interval 1 to 2. What about the initial conditions here? We have already seen that the solution y2 for this initial value problem must satisfy the initial condition that y2 at the initial point 1 must be 0 and y2 dashed at 1 can be arbitrarily prescribed, but it should be a non-zero value. So, we prescribe y2 dashed at 1 to be equal to 1. So, we have described the two initial value problems appropriately and denote the solutions of these problems respectively by y1 and y2. So, let us solve these two initial value problems by Runge-Kutta method of order 4. So, what do we have to do? We have to divide the interval 1 to 2 into a number of equal subintervals. So, let us divide the interval into 10 equal subintervals. What is the width of each subinterval? It is going to be 2 minus 1 by 10. So, 1 by 10 will be the width of each of the subintervals, and so the points in the interval 1 to 2 will be 1. Then 1 plus 1 by 10, that is 1.1, 1.2, 1.3 etc. up to 1.9 and finally 2. These are the points in the interval 1 to 1 at which we seek an approximation to solution of each of these initial value problems. How do we do it? We want to use Runge-Kutta method of order 4 to obtain the solution. So, I shall denote by u1i the approximation of y1 at xi and by v1i the approximation of y2 at xi, and denote by wi the approximation of y at xi. What is y at xi? We have already seen. We have to generate the solution of the boundary value problem by a linear combination of the two solutions of the two initial value problems, namely y of x is y1 of x plus k times y2 of x, where k is given by beta minus y1b by y2 at b. So, that is what I have written here. So, if y of xi is the solution at the point xi in the interval 1 to 2, then y of xi is y1 of xi plus beta. What is beta? It is y at 2. Just see what is prescribed as y at 2 in the boundary value problem. Y at 2 is prescribed to be 2. So, beta is 2 minus y1 at b. What is b? B is the other end point of the interval, namely 2, by y2 at b, that is y2 at 2. Do we have a knowledge of these values y1 at 2 and y2 at 2? That is what we are determining now by solving the initial value problem which we have described above. So, the solution will give us y1 of 2 and y2 of 2. We can use here and find out what y at xi is. So, we said we are solving the two initial value problems by Runge-Kutta method of order 4. So, we have listed the solution of the two initial value problems in the following table. Before that, let us see the exact solution of the boundary value problem. So, it is easier to determine the exact solution of the linear boundary value problem, which is governed by the second order differential equation. So, it turns out to be y is c1x plus c2 by x square minus 3 by 10 into sine of log x minus 1 by 10 cos of log x, where c2 and c1 are given. So, we give the table in which the points xi at which the solutions are obtained are listed. So, namely starting from 1 and moving in steps of h, which is point 1, we have these points xi at which the solutions have been determined. For the first initial value problem, whose solutions we have determined, we have denoted by y1i, the second initial value problem v1i, and y of xi, namely wi, and the exact solution is listed in this column, and the last column gives you the absolute error, namely the difference between the exact solution and the approximate solution. So, this column gives you the solution of the first initial value problem at the xi. This gives you the solution of the second initial value problem, and we compute the linear combination of these two solutions and write down the solution wi in this column, and we compare this with the exact solution and compute the absolute error, and we see that our approximate solution matches very well with the exact solution, and the absolute error is negligibly small. The reason for this greater accuracy in this problem is because we have used a Runge-Kutta method of order 4, where the error is of order of h to the power of 4, and this results in greater accuracy of the approximate solution that we have obtained for this boundary value problem. Let us now consider another example, namely consider the boundary value problem, which is minus y double prime plus pi square y equal to 2 pi square into sin pi x, which is a linear boundary value problem where x belongs to the closed interval 0, 1. And now, what are the boundary conditions? they are Dirichlet boundary conditions and are prescribed as y of 0 equal to 0 and y at 1 is also 0. So, we want to apply shooting technique to solve this problem. So, we need to write down two initial value problems. So, let us write them out. The first initial value problem has governing equations to be given by the non-homogeneous differential equation for the boundary value problem. So, I have written down the differential equation as it is. What about the initial condition? Y at 0 should be taken as 0 and it is the same as what is prescribed in the boundary value problem. So, I have that condition written down here. What about y prime 0? It can be arbitrarily prescribed. So, we prescribe it to be 0. That completes the definition of the first initial value problem. What about the second initial value problem? We should consider the corresponding homogeneous differential equation for the boundary value problem. Namely, put r of x is equal to 0 and take the corresponding homogeneous differential equation, which is this. What about the initial conditions for this initial value problem? Y of 0 is 0, but y prime 0 must be prescribed as a non-zero value. So, let us take y prime 0 to be equal to 1. So, the second initial value problem is also defined. Now that the two initial value problems are known to us, we again solve these two initial value problems by Runge-Kutta method of order 4. So, what should we do? We should divide the interval in which the differential equation is defined, namely 0 to 1, into a number of equal subintervals. So, let us take the number of equal subintervals to be 4 and therefore, the step size will be 1 minus 0 by 4. So, h is 1 by 4. So, as before, we denote by u1i and v1i the approximate solutions of the first and the second initial value problem obtained using Runge-Kutta method of order 4. Then, if the approximate solution of the boundary value problem is denoted by w of x, then w of x is given by u1 of x plus k into v1 of x. And how do we determine this k? It is determined by imposing the condition that w at the other end point 1 must be equal to whatever that is prescribed in the boundary value problem. What is prescribed in the boundary value problem? It says y at 1 should be equal to 0. We want to find k such that w of 1 should be equal to 0. So, we compute w of 1, that is u1 at 1 plus k into v1 at 1, but this must be 0, that it immediately gives us k to be minus u1 at 1 and v1 at 1. Do we know these values? Yes, we solve the two initial value problems by Runge-Kutta method, starting from the initial conditions prescribed at 0 and move in steps of h, which is 1 by 4, and go to the point x is equal to 1 and obtain the approximations to the solution of the two initial value problems at that point, namely x is equal to 1, which we have denoted by u1 of 1 and v1 of 1. So, this will be known to us when we have obtained the solutions of the initial value problem, and therefore, k can be immediately obtained and k can be substituted here, and u1 of x plus k times v1 of x will give you an approximation to the solution of the boundary value problem at any x in the interval 0 to 1. In particular, at the xi's that we have chosen in the interval 0 to 1, the approximations to the solution of the boundary value problem can be obtained. So, let us see what the solution is. So, the results are presented in the following table, namely the xi's are such that they are equally spaced and the step size is 1 by 4. So, the xi's are 0, 1 by 4, half, 3 by 4 and 1. The solution of the first initial value problem denoted by u1 of xi are specified at these xi, and that of the second initial value problem denoted by v1 of xi are given here at these xi. And we said that k is the value of u1 at 1 by v1 at 1 into minus 1. So, u1 at 1 is this and v1 at 1 is this. So, this gives you the value of k. So, having determined k, what is the approximate solution to the boundary value problem? W of x is u1 of x plus k times u2 of x, and it is guaranteed to satisfy both the boundary conditions in the boundary value problem, because we have already discussed these details. So, the following table presents this approximate solution of the boundary value problem and the exact solution y of xi and computes the absolute error. What is the exact solution of this problem? It is y of x is equal to sin pi x. So, that column for the exact solution gives sin pi xi at these points xi. So, they are written down here. So, we now compare our approximate solution at each of the xi with the exact solution at that xi, and we observe that the accuracy is quite good. There is an excellent accuracy, or there is an excellent matching between the approximate solution and the exact solution, and the absolute error is negligibly small. And as mentioned above, this is because of the Runge-Kutta method that we have used, and the method is of order 4, and because the error is of order h to the power of 4, the solution that we have got for approximation matches well with the exact solution of the problem at any xi in the interval 1 to 2. In spite of the fact that the step size h that is chosen by us, namely 1 by 4, is not very small, we have been able to show that the accuracy is excellent. So, by solving the two initial value problems which are defined as described, and taking a combination of these two solutions, we have been able to generate the solution of the boundary value problem, and this technique is shooting technique for solution of linear boundary value problem, which is governed by the Dirichlet boundary conditions. One can also solve the linear boundary value problem with Neumann or Robin boundary conditions, similar to what we have done for the Dirichlet boundary conditions. We shall see these details in assignment problems. Coming to non-linear boundary value problems, using shooting technique is out of scope of this course, and therefore, we stop our discussion on shooting technique for the linear boundary value problems. And this completes our discussion on the numerical solution of ordinary differential equations. And let us summarize the different techniques that we have used in developing or in obtaining numerical solution of ordinary differential equations. We described first what an initial value problem for the first order equation subject to an initial condition, and obtained the solution of initial value problems, and we described a number of numerical methods, namely Taylor series method, Euler's method, Runge-Kutta methods of different orders, and any of these single step methods can be used to obtain solution of an initial value problem. And then we moved on to multi-step methods. We developed Adam Moulton multi-step method, Adam Bashforth multi-step method and Milne multi-step methods, which require information about the solution at a certain number of previous points in order to obtain the solution at the specified point. And we used these multi-step methods in the form of predictor-corrector methods and predicted the required solution and then used the corrector to correct this predicted value and successively used this corrector and obtained the solution correct to the desired degree of accuracy. So, these are all different techniques for solving initial value problems. And then we moved to boundary value problems and we focused our attention on linear boundary value problems. And we looked into the linear boundary value problems with Dirichlet or Neumann or Robin type of boundary conditions and described finite difference technique of solving the boundary value problems with any of these types of boundary conditions. And finally, we have taken up a shooting technique for solving a linear boundary value problem. And the basic idea in the shooting technique is to convert the given linear boundary value problem into two initial value problems with appropriate initial conditions and obtaining the solution of these initial value problems using any of the techniques that we have described earlier, and then combine these two solutions and generate the solution of the boundary value problem. When conditions on P of x and Q of x that appear in the governing differential equations of the boundary value problem are satisfied as given in the theorem, the boundary value problem has a unique solution and this can be determined using a shooting technique. This is what we have discussed in this class. So, these are all different techniques for solving either an initial value problem or a boundary value problem, and with these discussions we will close this section on numerical solution of differential equations. In the next class we shall take up the topic on numerical solution of equations of the form f of x is equal to 0, where f of x is either purely algebraic or transcendental. And we shall develop a number of direct as well as iterative techniques for solving an equation of the form f of x is equal to 0 and perform error analysis and see which of the methods that we describe is going to score over the other methods and what is the advantage of considering different methods which are either direct methods or iterative methods. We shall continue these discussions in the next class.